Hi, this is Tsung Tai Yeh. The topic I want to talk today is the kernel PCA in pattern analysis. We know PCA, principal component analysis, is able to reduce the dimensionality of data and classify data to recognize data patterns. You may say PCA has been able to handle various classification tasks very well. What is the problem of PCA? What is the kernel methods? Why should we add the kernel method into PCA? So in the following slides, I will introduce and account for this question. Okay, the motivation of the kernel methods. In the real world, we have a lot of nonlinear data, and we want to classify this data effectively. However, we can see from these two figures. The left one is the nonlinear data that consists of the two classes, the red one and the blue one. After performing the PCA, we find in the right figure, PCA cannot separate the nonlinear data very well because the PCA cannot find a linear separation in the 2D dimension no space with two data classes. So this is the reason why we want to add the kernel method in the PCA, because the PCA can help us to classify the nonlinear data better. The basic idea of the kernel method. So, what is the kernel method? We know it is hard to linear separate these data with different class in a low dimensional space. For example, in this space, we cannot find one linear separations to separate the blue class and the red class. So the kernel methods, the idea of kernel methods is to map the data from one dimension no space to another dimensional space, and that is often higher than the original one. In a new feature space, the data may become linear separatable. That is help us to use the linear classifiers to perform the classification. For example, in this new feature space, we can find one linear separation easily. So regarding to the feature mapping function, we can map the x1, x2, these two data vectors, to the z1, z2, z3 in the new feature space. And the original x1, x2 will become x1 square, square to x1, x2, and x2 square. Okay, what is the goal of the kernel methods? Sometimes the people may not know the exact feature mapping features file. The feature mapping function file that maps the data from the one-dimensional space to another one. How can we figure out the geometry features such as the distance and angles among data in the new feature space, which can help us to classify the data in the new feature space? In fact, from the equation 1, we can know, given a kernel function k of xz, and then we can know the inner product of the data in the feature space. In other words, we can use the kernel methods kernel functions to reason the geometry features of the data in the new feature space. So, in other words, we may not need to know the feature space phi, but we can use the kernel methods, kernel functions, to approximate the geometry space of data in the new feature space. So this is a good characteristic. So we only need to only need to get the kernel function, and we can use this kernel function to reason the geometry features of the data in the new feature space. Since this characteristic of the kernel methods, all we have to do is to pick out a good kernel functions. Then we can understand the condition or the status or the characteristic of the data in the new feature space very well. In addition, there are some popular kernel functions. For example, the polynomial kernel function and Gaussian kernel function. We can use this popular kernel function to reason the conditions or characteristic geometry features of data in the new feature space. Okay. After we know the kernel tricks, we can start to step in the kernel PCA. So in general, the kernel PCA also keep the spirit of PCA, but the kernel PCA adds kernel function in. So let us see how to mix the kernel function in PCA in the following slides. At first, I want to define the covariance matrix of data in the feature space. It's the product of x and the x transpose and divide by the n. And this equation is similar with the covariance equations used in the PCA. And second, I want to compute the principal components by solving this eigenvalue problem. So the CF is the covariance matrix of the data in the feature space, and the V is the eigenvector, lambda is the eigenvalue. So in this slide, what I want to show is to see if the eigenvectors can be expressed as the linear combination of the future vectors and the one scalar or the one parameters a alpha I. So there is one proof to prove if we can see the one eigenvectors can be expressed as the linear combination of the feature vectors. So in the beginning, we know the C times V is equal to the lambda times V, and we can rewrite this CF based on the equation 3. We can write in this way: times V, the summation times V, and then we can just put the lambda in here and rewrite in this way, and then we can put this xi transpose vector in here, and then we can get the new equations. Is the eigenvector is equal to the summation alpha I times xi. So this alpha I can be represents this parameters. So we can see the eigenvector can be expressed as the linear comparison of the data in the feature space in this proof. Okay, in this slide, I want to see if I can add the kernel functions in the eigenproblems. So there's one trick to prove this idea. As first step, I just multiply the phi of xi in the both sides of these eigen equations. So they will become in this way. And then we just expand the original equation formula into the equation 7. We can see this v is equal to this one times the phi of xk, and this cf is equal to this one, the summation of the alpha I times xj, and to v equal to this one. And then we just define the matrix K as the kernel functions, and the kernel functions can be expressed as the phi xi times xj. And then based on the equation 7, we can get the new equation, the n times lambda times the k and alpha is equal to the k squared times alpha. And after eliminating this k, we can get the new eigen decomposition with the kernel function. We can get the n times lambda alpha is equal to the kernel alpha. So in this slide, we just get this new eigen decomposition equation formula that is integrated with the kernel function. Okay, this is a good proof. In this slide, sometimes the future vector x may not be zero mean, so we can perform the normalization to center feature vectors. So we can get the new centering feature vectors while subtract the mean of the feature vectors. In addition, the centering kernels also become the results of the equation 10. We just rewrite the original equations and to subtract the mean, and then the new kernel function will become this one. So then we can get the center kernel function ker hat. Okay, let us see the simulation results of the kernel PCA. So here I want to show the results of the kernel PCA classification. Compared with the previous PCA classifications, we can find the kernel PCA is able to separate the data into the two classes from the right figures. So this is the proof to present the kernel PCA is able to classify the nonlinear data better than the PCA. Okay, Let us summarize the workflow of the kernel PCA. At first, we need to decide one kernel function. For example, you can use the polynomial kernel and Gaussian kernel. Second, we need to construct the normalized kernel matrix of the data based on the normalization formulas and get the centers kernel matrix. And third, we want to solve the eigenvalue problems based on the following formula. As that, we can represent the output data y given by the following formula. So there is only 4 steps we need to perform in the kernel PCA. Okay, in conclusion, from this tutorial slides, we can know the kernel method is to map the data from one dimensional space or the low dimensional space to another or higher dimensional space. And then we may find the linear separation in high dimensional space. In contrast with the PCA, the kernel PCA adds kernel tricks into PCA and enable the kernel PCA to support the classification of the nonlinear data. Okay, if you are interested in the kernel PCA further, you can try to refer the following reference. Okay, thank you.